All right, welcome. Food is not here yet, so we'll start on time and we'll take a 5-minute break in between so you can get food. Today we're very happy to have Nathan visiting us. Nathan is an assistant professor at Boston University. He received his PhD from University of Washington, advised by Anna Carling and Cheyenne Ovis Garrett in 2023. He was a postdoc at the Institute for Advanced Study for a year. He's an expert on approximation algorithms, particularly for graph problems, including the famous results for TSP. He's a winner of the Stock 2021 Best Paper Award, as well as a European Association for TCS Distinguished Dissertation Award. All right, Nathan.
All right, thanks a lot for the introduction. And yeah, great to be here. So let's get into it. I'm going to be talking about ghost value augmentation for K-edge connectivity. And you know, it's almost Halloween, so here's my Halloween version of the slide. You know, we're 2 weeks out. If we were like 1 week out, this would be scarier. But okay, it's not too scary. Okay, they've changed a little bit from the last time. Okay, so I'm going to give two different introductions. The first introduction is geared more towards like combinatorics, and the second will be geared more towards like solving a computational problem. So you can pick the one you like better. Let's do the combinatorics intro first. So there's a field actually called fractional graph theory, and in this field you work with graphs that instead of having each edge is like either existing or not existing in the graph, it has some fractional value between 0 and 1. Yeah, so this is like, you know, clearly different from a normal graph because you can have fractional values. Here's an example fractional graph. So I have some edges can have value 1, but also some edges can have value, say, 1/2. And given these fractional objects, you can ask questions about them. You can study their properties. One nice property that I like about graphs is studying their edge connectivity. So for this example, we're going to talk about K-edge connectivity, which means that if I look at any cut in the graph, there's going to be at least a weight of K crossing that cut. So if I sum the value of these edges crossing the cut, I sum their X value, I should get some value at least K, okay, for every cut. So this example turns out to be 2-edge connected. You know, another way to think about edge connectivity is like if you have any two pairs of vertices and the edge connectivity is K, I can send okay, we can pause. Okay, cool. All right, so you can think about this while we're this idea. Here's a question. You can think about this for like during the food. If I'm given a fractional graph, can I write it as an average of real graphs that are all K-edge connected? Okay, cool. Should I keep going? All right, I'll keep going. All right, so you had a really long time to think about this question. Does anyone see if it's true for this graph or not? Yeah. Sure. Yeah.
Okay.
Yeah.
I would say yeah.
Yes. Okay. Cool. All right. Well, here's a solution. Maybe what you had in mind. I can write this as an average of these two graphs, right? And both of these graphs are 2-edge connected, and they're not fractional. So for this example, the answer was yes. Okay. And this is actually a very general research question. You can look at a fractional graph. You can say, I want to round it to some random integral graph. And I want to do that so that every edge is included with probability XE, right? The fractional weight. This is a natural thing you'd like to do. And then you can ask, like, what properties of the fractional graph can I ensure hold for all the integral graphs? And maybe you'll lose something. In this example, we didn't lose anything. But you know, maybe in general, you can ask, maybe we can only approximately have the properties of GX hold. Okay, but still we have this question. Is it true in general? It was true for our one example. It turns out the answer is no. Okay. Yeah, does anyone see a bad example? Let's see.
Triangle, one connected.
Perfect. Triangle. So if I put 1/2 on every edge, this is a one-edge connected graph. But the number of edges is like 3/2. So if I try to write this as an average of graphs, like one of them has to have only one edge, and obviously that's not going to be connected. Okay. And if you're trying to construct an example for even k, this works for all odd k. Try to get an example for even k, you can use this graph. You can also convince yourself that this can't be done. Okay, so what about upper bounds? We know we can't get k, but can we get something? It turns out a very old result, it's called the Nash-Williams theorem from the 60s, will give you k over 2. Okay? And in terms of lower bounds, actually this is the best example we have. So maybe the answer is k minus 1. The best we know is k over 2. There was no progress on this question. In 2010, Pritchard wrote a paper that conjectured that actually k minus order 1 should be possible. And that's our main theorem. We proved that you can do k minus 10. Okay, so given a fractional graph, which is k edge connected, you can write it as an average of k minus 10 edge connected graphs. All right, so that was the combinatorics intro. Maybe that already made you care about this question, this theorem. But if not, let's go into some computational problems that are related to this. Okay, so the natural question we should look at is this KECSS, or k-edge-connected spanning subgraph problem. Here I'm going to give you a graph with some edge weights, so like this one, and some parameter k. And what I want you to do is pick the cheapest subset of edges f, such that the graph with vertex set v and edge set f is k-edge connected. Okay? So this is the problem. Maybe you haven't heard of this problem. I promise you know it for k equals 1. For k equals 1, this is the minimum spanning tree problem, right? Okay. So you might say, oh, it looks polytime solvable, like it's true for k equals 1, so probably it's in P. It's not in P. So for k at least 2, this is a NP hard problem. Actually, it's APX hard in a fairly strong sense. So there's some constant, like 1.01, such that for any k, there's no approximation algorithm with ratio better than 1.01. Okay?
The hardness was probably known well before then. I know we're
yeah,
seeing this, right? So.
I think maybe this is a slightly more general result in the APX hardness, but yeah. Okay, so here's an example solution for k equals 2, and you can kind of check it's not as clear why this is an optimal answer, right? Okay, so what's known about this problem? So the best known approximation algorithm for KCSS is a 2 approximation. So it's some polynomial time algorithm that produces a solution of cost at most twice that of the optimal solution. And this has actually been known since the 80s, but one nice approximation algorithm is through iterative rounding, and it's from Jane. And we'll be talking a bit more about iterative methods in this talk, so that's why I'm bringing up this result. And a major open question is, can you get a better than 2 approximation for KCSS for any k that's at least 2? So this is even open for like k equals 100, k equals 1,000,000, whatever. We don't know how to do better than 2. Okay, but we couldn't make progress on this question. So we asked a different question, which is, all right, let's think of k being a very large number, like 1,000. Maybe if you're trying to create a highly connected network, maybe you're okay with losing a little bit on the connectivity instead of losing in the cost, right? So the question is, can we find a k minus order 1 edge connected graph that has cost no more than that of the optimal k edge connected graph? And our main theorem, which is actually just a corollary of what I told you in the combinatorics part, is that we can get a polynomial time algorithm that produces a k minus 10 edge connected graph with cost no more than that of the optimal k edge connected graph. And I think this is actually pretty useful. Again, like the example of k equals 1,000, if you're some company trying to build a highly connected graph, you have two options. Build a 990 edge connected graph for some cost C, or build a 1,000 edge connected graph for twice the cost, 2C, right? So losing 10 in connectivity is probably more attractive than losing a lot in cost. So how do we prove this? We first relax the problem using a linear program, which is just this connectivity linear program, which says that I want to minimize the cost of my graph, and I want every cut in the graph to have at least a weight of k going across it. And now here are my sort of decision variables, xe. If these were binary, then this would solve the problem optimally, right? I would just be saying, give me a graph that's k-edge connected and has minimum cost. But when we relax this to have variables between 0 and 1, now we get an LP. And it turns out this can be solved in polynomial time. And you might be like a bit suspicious because there are exponentially many constraints here. But this has a polynomial time separation oracle, so we can use the ellipsoid method. Right? So the separation oracle is just you check the global connectivity of the graph. If it's below k, you return a cut that's below k. OK, so here's an example of the solution for k equals 2. And maybe it looks familiar, right? This is just a fractional graph. Okay, this is gx. So this connectivity LP allows us to optimize over the set of fractional graphs instead of the set of integral graphs. And now our main technical theorem is that given a solution to this LP, given a fractional graph, we can round it in polynomial time to an integral k minus 10 edge connected graph of no greater cost. And this clearly implies the main theorem because I solve this LP and then I round it and I'm done. Okay. This also gives us a corollary for a very related problem known as KECSM, or the k-edge connected multi-subgraph problem, which is the same as KECSS, except that I'm allowed to buy each edge as many times as I want at the same cost. Okay, so if I have some graph, this is a valid 2 ECSM, but it's not a valid 2 ECSS because I've used this edge twice. So for a long time, the best known approximation algorithm for KECSM for any k was a 3/2 approximation. But in 2022, with Carl Noveskaran and Zhang, we got a 1 plus order 1 over square root k approximation. So we got something that gets much better as k gets larger. And I just want to point out, remember that this result cannot be true for KECSS, because as I said in the beginning, it's APX hard for all k, right? So if I chose k, you can't get better than a 1.01 approximation even for k equals 1,000,000. And so this would contradict that if it was true for KECSS. But there's an open conjecture, which is that actually this can be improved to 1 plus order 1 over k. And our main technical theorem immediately gives this as well. So it gives a 1 plus 10 over k approximation for this problem. And you might see kind of immediately how this can be done, right? So I start with some LP solution, which is k-edge connected. And now I'll take every edge, and I'll scale it up by a factor of 1 plus 10 over k. Now I have some fractional graph that's k plus 10 edge connected, because I've scaled everything up by this amount. And now I can apply my rounding theorem and get back a k-edge connected graph. And you might say, OK, why can't you do that for KECSS as well? And the thing is, when I scale up my edges, some edges might actually exceed 1. So I might use those edges more than once. Okay? And that's exactly why KECSM is easier than KECSS. Okay, any questions about what we've done so far? OK, cool. One final thing we prove is that, so there's a question also asked in this paper by Pritchard, which is if there's a matching hardness result to this conjecture. So can you do better asymptotically than 1 plus order 1 over k? And we proved that you can't unless p equals np. Okay, so this is tight up to the constant 10. So just to summarize, what we talked about so far in this TCS intro. We talked about two problems, KCSS, KCSM. The difference is just whether you can take every edge more than once. For KCSS, we have this 2 approximation. And now we've kind of complemented this with a sort of resource augmentation-like result. I can get a k minus 10 edge connected graph. It costs no more of the optimal k edge connected graph. We also know that there's no approximation algorithm with ratio going to 1 as k grows. For KCSM, we now know matching upper and lower bounds, 1 plus order 1 over k is the right answer. And I just want to point out that for the unweighted case, things are a lot easier. So if all of the weights of the graph are 1, then we've known for a long time that there's a 1 plus 2 over k approximation for KCSS, which actually shows that these problems are fundamentally different, right? So the weighted and the unweighted case, again, there's no pita, it's APX hard, but the unweighted case is not APX hard. So these are fundamentally different. And what we've now showed is that actually for KCSM, the unweighted case and the weighted case are the same up to constants. All right. So just to unify the two intros now, we have this main technical theorem. The first one is a rounding theorem. Given a solution that's k edge connected, you can round it to a k minus 10 edge connected graph of no greater cost. The second was this averaging theorem. Given a k edge connected graph that's fractional, you can write it as an average of integral graphs that are k minus 10 edge connected. It turns out these are equivalent statements. So one is true if and only if the other is true. I won't prove that, but it's not too hard to see. OK, so before we start diving into the proof, I just want to talk about the classic approach, which would be this trying to extend this result from the 60s of Nash-Williams, which I mentioned in the combinatorics intro. So Nash-Williams proved that any fractionally k-edge connected graph can be written as an average of unions of k over 2 edge disjoint spanning trees. Okay, so I can write my fractional graph as an average over these unions of trees. And you can ask whether this can be improved. Maybe I can get k over 2 plus 1 disjoint spanning trees. But you can pretty easily see that you cannot do this. So if you have a k-regular k-edge connected graph with n vertices, it's going to have kn over 2 edges. But every spanning tree has like around n edges. So you can't hope to pack more than k over 2 edge disjoint spanning trees in these averages. So we're going to have to do something different. And that's what the rest of the talk is about. How do we prove this theorem? Let me check again. Any questions on what we talked about so far? OK, not going too fast. All right. So the technique we're going to use to prove this theorem is the iterative relaxation framework. This is a line of work that was kind of initiated by Jane in 2001, but in the form I'm talking about it, it's from Singh and Lau in 2007. And it's a very beautiful, simple idea. So just consider a linear program. Let's say we have n variables. We have some trivial constraints that just say that every variable should be between 0 and 1. And then we have some number m of kind of non-trivial constraints. So in this LP with 2 variables, we have, let's see, 4 non-trivial constraints. And n is 2. And here's a very basic fact that probably most of you know. So in any basic feasible or extreme point solution to a linear program, or equivalently any like vertex of the resulting polyhedron you get, there are exactly n linearly independent constraints met with equality that uniquely define this point x. So for example, let's say I have this polytope. I'm optimizing in this direction. If I get some optimal solution, it's going to be characterized by 2 linearly independent tight constraints, because n equals 2. Okay? It's a very simple fact, but it's actually what underpins like all of these amazing algorithms that come from iterative relaxation, iterative rounding. So here's a simple observation. Sounds almost silly. If n is greater than m, so if the number of variables is greater than the number of non-trivial constraints, then at any vertex, any basic feasible extreme point solution, there's always a trivial active constraint. There's going to be some xi that's set to 0 or set to 1. So pictorially, it's like, OK, if n equals 2 and I only have one constraint, then whenever I optimize, I should hit a face of this box, which is telling me that my variables are between 0 and 1. OK. This actually suggests an algorithm, which I'm going to call like the iterative relaxation algorithm or framework. So you solve your LP, get some extreme point solution. And now you check if there's a variable that's set to 0 or 1. If there is, you delete that variable and kind of update the constraints accordingly. OK, so let's imagine that happening. Kind of case 1, we hit a face of these box constraints, asking us for the variables to be between 0 and 1. Then I'm going to fix this variable to be, in this case, 0 for the rest of the algorithm. And I'll continue rounding on this lower dimensional space. Right? So now I've like reduced the dimension from 2 to 1. Or to do a slightly more involved example, like I have 3 dimensions. Maybe I optimize, I hit a face of this cube. And now I continue rounding in this 2-dimensional space. OK? So the first case is very easy. Like I'm just fixing a variable and going to a lower dimensional space. The interesting thing that can happen is maybe I hit n linearly independent tight constraints that are not trivial. Okay, so for example, we already saw this. Here, n equals 2, and we can actually hit a vertex that has no variables set to 0 or 1. In this case, what should we do? It turns out to depend on the problem, but the iterative relaxation framework says you should delete one of the constraints that's tight. So this is problem specific, but let's say I delete this constraint. I decide I don't need it anymore. Then I re-optimize. I find another, I get to case 1 again, I get to case 2, and so on and so forth. Eventually, I output some integer point. And the cost of that integer point must be at most the cost of the point that I started with, because all I've done is fixed variables and dropped some constraints and re-optimized. So I can never get a solution that costs more than what I started with. So the core of this argument, right, like the only thing that we did was decided, when we were in this case, what constraint do we drop? And basically what we have to prove is that whenever you're in this case, there's some constraint that's sort of approximately satisfied by the variables that are already set to 0 or 1. So you kind of look at this like lower dimensional space that you're in now that you've fixed certain things to be 0 or 1. And you say, OK, I'm going to check all of my constraints at this point. And I'll find one that's approximately satisfied by the variables I've already set, or is kind of approximately implied by the remaining constraints. And then I'll delete it, I'll make progress, and I'm happy. OK. So it was a pretty quick tour of iterative relaxation, but does it make sense? Any questions? See some nods. OK. OK, so let's try to apply this to our problem, the k-edge connectivity problem. It turns out there's a very natural approach that's worked for other problems in the past. So you take your graph. Let's say this is a vertex, an extreme point solution to my LP, and I'm wanting 2-edge connectivity, right? Remember, this is the LP that we're solving. There's a lot of tight constraints. The tight constraints correspond to all of the sets that have exactly 2 edges in them. And you can check all the things I've drawn and the vertices, actually, are sets that are tight. Okay? There's a lot of tight constraints. It turns out, through very standard techniques, you can take the set of tight constraints and so-called uncross it to obtain a laminar family which spans all of the tight constraints. And a family is laminar if for any 2 sets in the family, either they don't intersect at all, or one is a subset of the other. Okay? So if you want to think about it like pictorially, like I can draw circles in the plane with my sets such that no 2 of the lines cross. Okay? And I'll sketch now kind of how this works. This is maybe a bit unclear. let's just see if it works in this case. So I've taken this. I'm promising you that this laminar family actually spans all of the tight constraints. So let's check for let's say, this one. It turns out I can write this set T using like the submodularity of the cut function. I can write it as, actually this is a posi-modularity, but okay. This is the edges in S minus T plus the edges in T minus S minus the edges in delta of S. Okay, so T and S are two of these like crossing sets. I want to say that T is actually spanned by the constraints in my laminar family. And this formula shows you that it's true. And you could check it, right? So, okay, I want to get the edges of T. Okay, so I have these two edges. They're going to appear in T minus S, so I'm good. I get these two edges from T minus S, but I also subtract them from S. So I'm happy. I don't get these two edges. These two edges, they appear in S minus T, but they also appear in T, so I'm good. And finally, these two edges appear in both S minus T and S. Okay, so this is a correct. We've already spanned T. And if you prefer to think about it just like as some more abstract thing, I can associate each of these constraints with just the set of edges that's in those constraints. These are kind of like, these should be like rows of the matrix, but it's easier to think about them as vectors. I'm just showing like a linear dependence between these rows. Okay. These are the same thing. And I think, so we have the rank of the collection of constraints that we get of this form. X of delta of S is at least K. We know it's at most the size of some laminar family, right? And actually, you can check that this is a simple exercise, that the maximum size of a laminar family is 2n for any graph. Okay, so that means that the rank of the set of constraints coming from my laminar family is at most 2n. But I have m edges, maybe like n squared edges. But this means that all of the remaining constraints defining my extreme point must be coming from the box constraints, the constraints asking for my variables to be between 0 and 1. So this actually says that very few of the edges are fractional, lie between 0 and 1. Questions about this? I think this is it's an important point. So we start with our set of tight constraints. We show that they can be represented, spanned by a single laminar family, which has small size, at most 2n, which means that the remaining tight constraints must be of the form x equals 0 or 1, right? Which means that the graph is actually very sparse in the number of fractional edges. Okay.
Sorry,
Yeah.
I
Yeah.
forgot that what L is, but basically it means that we can compress the whole exponential number of constraints into like n constraints. Right?
So it's not quite that. It's almost that. It means that we can compress all of the tight constraints,
Yes.
which actually you can prove, like a nice fact is that actually there's at most n squared of these. But yeah, so you start with your tight constraints. Turns out there's at most n squared of them. But then you show that they can be uncrossed to get this laminar family of size order n.
Just and because there are n square variables,
Mm-hmm.
and we can basically get rid of the n square minus n ones with the
Exactly, yeah.
iterative.
Exactly, yeah.
I see.
So almost all of the variables go away. We have like something of linear size.
Thank you.
Yeah, thanks for the question. Okay, this is sometimes called like the rank lemma. But yeah. And I think like pictorially, a nice picture to have in mind is maybe we have, okay, in 3 dimensions, we have some point that looks like this. So there are many tight constraints at this point. And they're not necessarily redundant, right? Like I can't just like delete this face from my polytope. But if I want to define this point x, I only need 3 of them, right? So I tried to draw hyperplanes in 3 dimensions and I failed. So what's going on is like, okay, in 2 dimensions, I have like some tight constraints. So I have 3 tight constraints. And I'm just choosing like 2 of them that span the remainder. So these two constraints are kind of an analog of my laminar family. And this purple constraint is something, it's an analog of being spanned by my laminar family. Okay, so here's our general recipe. We've talked about the first part. We argued that the tight constraints can be uncrossed to give us this laminar family. And now we're going to use this, which basically says that our graph is very sparse, to show that some constraint in this laminar family is already very close to satisfied, in the sense that the edges across it, most of them are already set to 1. So k minus order 1 of them are already set to 1. You might not be convinced of this quite yet, but I'll sort of sketch the argument here. So, okay, we know there are only like L fractional edges, like 2n, let's say. And we can prove that the average fractional edge is in only order 1 of the sets in this laminar family. Okay? But, that actually means that the average set in this family only has order 1 fractional edges. Okay? So that must mean that one of these sets has only order 1 fractional edges, since the average is only order 1. But that means that the remaining edges must be integral, because each cut has to have k edges going across it. And the amount of mass I can collect from my, let's say, 5 fractional edges is at most 5. So the remaining k minus 5 edges are integral. So if you think back to iterative relaxation, the framework, what we were looking for is when I get some tight constraint, when I get to some vertex, I want to show that there's a tight constraint that's already very close to satisfied. And this is saying that actually one should exist. Okay? So this is what you would try if you were trying to solve this problem with iterative relaxation. There's some good news. So uncrossing is this first step we did. And it works on the set of minimum cuts of any graph. And remember our LP, it's saying it's a k-edge connected graph, and the tight constraints are exactly the minimum cuts of this graph GX, the graph, the cuts with the smallest amount of edges going across. So that's good. But there is some very bad news, which is that after we drop a constraint, the minimum cut of the graph can actually decrease. Because I had some constraint that was mostly satisfied. It had k minus 5 integral edges. But then I just removed that constraint from my LP. But that means that the connectivity of the graph in the next iteration, when I resolve my LP, can drop below k. And now it turns out that uncrossing no longer works. So let's see why this happens. Okay, so let's kind of sketch this first fact about uncrossing. So 2k, let's say I have two tight sets, S and T, and the minimum cut of the graph is k. I have two tight sets, S and T. Now by posi-modularity of the cut function, or this is true for any symmetric submodular function, it's at least the size of S minus T plus the size of T minus S. Okay, and you can pretend there's an x, taking the x weight of each of these sets if you'd like. But now, since the minimum cut of the graph is k, each of these things are at least k. Okay. I want to take T to be somehow a minimal set that's not spanned in some sense. I can make this formal. So I can assume that actually these other two sets are already spanned by the laminar family. Right? So I want a minimal counterexample. I'm trying to say that my laminar family spans everything. And I can assume now that these sets, they're kind of smaller, so they should already be spanned by the family. But now actually we span T, because these are both at least k, but we have an equal to k over here. So these are all equalities. But then that says that T is just equal to this set plus this set minus this set. Okay? So that's why uncrossing works when the minimum cut of the graph is k. But now the minimum cut of the graph might drop below k. And now you try to do the same thing. And we get some bound like k minus 10 here. So these are not equalities. So you're not going to be able to span T, because these are, there might be some other edges going on. This is a very delicate operation, and we've violated it even by a little bit, and so you no longer get this linear dependence. Let's give an actual example of what's going on. Okay, so let's say I have two sets S and T, and let's say that previously in the algorithm, I dropped sets S minus T and T minus S, okay, because they had many integral edges. And you can see here they did. They had k minus 10 integral edges, which we'll say is our threshold because we're shooting for k minus 10 edge connectivity. Okay, but then you can check that, delta t is just not equal to this. In particular, you have this edge A, which appears like as a -1 on the right-hand side. Right? This edge A is not in s minus t or t minus s, so I'm just subtracting it, and this linear dependence just doesn't hold. Okay, so let's go on to the solution. We probably won't get through all of it, but let's at least get the main idea. So what we're going to show is that either we can uncross, so we can successfully uncross our set of tight constraints. Then we kind of use the argument we said from before. So there should be some set in this laminar family that has very few fractional edges going across it. Okay? So as long as we can uncross, things are good. We get sparsity. In this case, we're going to take a minimal tight constraint that has this property. We're going to drop the constraint, and then we're actually going to contract the set to a single vertex. It's not totally clear why I'm doing this yet, but that's the procedure. In the second case, we're going to show that if you cannot uncross, there actually exists two vertices in this possibly contracted graph that have very close to k over 2 edges going between them. So between like k over 2 minus 10 and k over 2, but strictly less than k over 2. So I have these two vertices that are like very, very well connected. In this case, we're going to perform our spooky thing. We're going to do a ghost value augmentation and just tell the LP that the value of this edge is k over 2. Okay. And you notice like I'm cheating here. Like maybe this is k over 2 minus 10, and I'm in the KECSS problem here actually. So I can't just like take edges more than once. Maybe there are not k over 2 edges between these two vertices. So that's why it's kind of a ghost value augmentation, because the edges may not exist, but I'm going to do it anyway.
Can you give an intuition for k over 2 instead of like k?
Yeah, so like actually if you have a sort of k-edge connected graph, you should never really add more than k over 2 edges between any pair of vertices, because the cut containing the two vertices should have k edges going out.
Okay.
And so it'd be kind of a waste to like do more. That's kind of the simple intuition, but yeah. And really, like the key observation of this paper is just this fact. It's that if the only cuts of the graph are the vertices, sorry, the only cuts below k in the graph are the vertices. This is like why I can't uncross, right? Because if every cut in the graph was at least k, then my tight constraints would be minimum cuts. So if the only ones are the vertices, then the only barrier to uncrossing is pairs of vertices with this weird property that they're very highly connected, but not quite k over 2 connected. Okay, it's a very strange fact, but we discovered it, and it's like we were like, okay, I guess this solves the problem.
So you're saying if it happened that for any two vertices, the connectivity was k over 2 between those two vertices, then that implies that there are no such bad vertices with small cuts. Is that right?
If there exists one pair of vertices like this?
Let's say let's say there's no pair of vertices with
with
less
this
than
property.
k over 2.
Minus order 1 or whatever.
With even less than k over 2. Suppose there's no vertices.
Oh, I see.
Vertex pair with less than k over 2.
Yes, that's true.
Less.
Yeah, then you can
That
uncross.
implies that there are no bad vertices at all.
That's right. Yeah, then you can uncross, and you're happy. Yeah. Actually, I think like in this case, your graph is probably just a cycle with k over 2 edges everywhere. But yeah. But yeah, basically what we're saying is like maybe a stronger thing of what you're saying is maybe if all of the pairs of vertices have like less than k over 2, like k over 2 minus 100, then you can successfully uncross. Like we have no issues. Yeah. Yeah, and so why do I get to assume that the only cuts below k are the vertices?
You shrunk them.
It's because I contracted, exactly. So it's because in this first step, we actually contracted the set. Okay. So Ellis,
And once you've contracted it, do you know at that point that the stuff that you contracted away is all okay?
So that is like, we have to prove it, but it is true. So it turns out that because we're going to take a set that has very few fractional edges going outside of it, and it's minimal, it must be integer inside. So the minimality says that actually inside of the set, all of the edges are 0, 1. The second thing is that we have at most order 1 fractional edges going into the set. So the only thing that can actually change in this graph is like a little order 1 part. So really, like, the connectivity is already very, very good in this whole subgraph. And I'll explain that a little bit more formally if we have time. But yeah. Okay. So Ellis drew this nice picture of the situation. So case 1 is like we're happy, we can uncross. Then we're going to find some minimal set with very few fractional edges. Then we'll just contract it to a single vertex. We'll argue later that the connectivity of the graph after uncontracting and solving on the remaining graph is still good. Or if this is not the case, we can't uncross. There's a reason we can't uncross, and it's because of this pair of vertices that's very highly connected, but not quite k/2 connected. And then we apply our ghost value augmentation. Okay, so let's talk a little bit about case 1, when we can uncross. So then there exists some minimal tight constraint S with a small number of fractional edges going across it. In this case, we're going to drop the constraint corresponding to S, contract it to a single vertex. Okay, so since delta of S has few fractional edges, has many integral edges, so set S itself is obviously safe. It's k minus order 1 edge connected, no matter what happens in the rest of the algorithm. Secondly, since S is minimal, this means that all edges inside of it must be integral. Okay? If there was some constraint some edge inside it that weren't integral, there must be something in this linearly independent basis that contained that edge, right? But there's no set inside of it, so there can be no such set. Okay? So everything inside has already been dropped. For example, we've already dropped the constraint corresponding to all of these vertices. Okay, so all the cuts that are actually inside S are safe for the same reason that S was safe. All the edges are integral except maybe these edges leaving S. The final thing that's a bit tricky to see, and I won't really give the full proof, is what about sets that actually cross S? Right? When you contract a set, in one sense, you're actually really dropping all the sets that cross it as well, which makes things a bit tricky. I'm not going to prove this. I'm actually going to give you a non-example of why we drop sets that have few fractional edges and not sets that have many integral edges. So one thing you could have imagined is I'm actually happy to drop a set as long as it has like k minus 10 integral edges, because then it seems like it should be safe to drop it. It turns out it's not true. You can't drop this set because of crossing sets. And I'll give you a non-example. So here we have this set S. And S looks great to me, like it has k minus 2 integral edges. I should be happy to drop it and contract it. There's all these fractional edges hanging around, but like it seems like it should be fine. But now let's contract. Let's suppose we contract S and resolve. Maybe what I did was I took all of these edges, set them to like k/2, and I took all of these edges, I set them to like k/2. So I got this graph, right? So this is just a single vertex, right? So after I contracted and I resolved, this is a plausible solution that my LP could give me in the next step.
What do you mean set them to k/2? You mean sort of collapse them into one edge with weight k/2?
What I mean is that in the next iteration of the algorithm, the LP could decide to move a bunch of mass onto these edges, like maybe there are like k/2 edges here, and they're all set to like 1/n. Right. In the next step, the LP could set them all to 1. Right. So now this edge corresponding to this thing could actually have value k. Right. And now maybe the LP actually sets all these edges to 0, which is actually fine, because in this graph, this is still like k edge connected. But now when I like uncontract, I got this solution. Let's say this was like the full solution on the rest of the graph. What was my solution here? It actually looked like this. But now t has size k over 2. Okay. So this is like a kind of proof through non-example. This is the only thing that can go wrong.
You mean when t has size?
T has
Delta
connectivity.
t?
Yeah, it's delta of t has connectivity k over 2. Yeah, thanks. Yeah. Yeah, so this is like way, I want k minus order 1, I'm getting k over 2. It turns out like this is the only bad thing that can happen. So as long as S had few fractional edges leaving it, then somehow the sets crossing it cannot change too much as well. Okay? I won't prove this, but hopefully you can see why, at least why we made the choice that we did, that we dropped sets that only have few fractional edges. Okay, yeah. Okay, in the second case, we do our ghost values. So let's return to our picture that we said before was bad. Okay, so I told you that we must have dropped S minus T. And we must have dropped, we must have dropped S minus T, and actually we also dropped S intersect T, because they had many integral edges. And that was it turned out to be kind of the reason that we couldn't uncross here. But now, since I dropped them, they must be vertices, because whenever I drop something, I contract it. But, okay, now this actually has the criteria we want. These two vertices share k over 2 minus order 1. And so we can apply a ghost value augmentation. Okay? So this is a bit, of course I haven't proved this for you. But it turns out that whenever you fail to uncross, the reason is that two of these sets have connectivity below k. Like two of these chunks have connectivity below k. Otherwise, you can actually successfully uncross. But if two of these chunks have connectivity below k, they must be vertices, because whenever we drop a set, we contract it. But then actually, the structure of crossing cuts that are close to minimal, that are close to minimal, because we have now a k minus 10 edge connected graph. So the structure of cuts that are close to minimal, actually, these edges are very large. They're very close to k over 2. This is something you can easily prove. But since two of them are vertices, these edges are large, that gives us a ghost value augmentation.
What do you actually do as a ghost value? You change the LP?
So we change x, and we just add a constraint that this edge is equal to k over 2. And we say, this is what you believe now, even if this is not the truth. Yeah.
You're imposing a new constraint on
Yes.
the LP.
Yes, yeah. So we're adding something that says x uv is equal to k over 2.
Can't that increase the cost?
It does increase the cost, for sure. But the thing is, at the end of the algorithm, I'm going to drop all the ghost value constraints and just return whatever the value of the edge was before I added the constraint. And of course, that's going to make the connectivity of the graph go down, because it was k edge connected or close to k edge connected when I had the ghost values. But these edges weren't really there. I was kind of adding 4 ghost edges here that at the end of the algorithm, of course, I cannot return because it increased my cost. But what we prove is that, I only increase edges by a kind of order 1 over k factor, right? So this edge was k over 2 minus 4. Now I'm making k over 2. So at the end of the algorithm, when I go from k over 2 to k over 2 minus 4, I'm only changing things by an order 1 over k factor. So actually, after removing the ghost edges, the connectivity of the whole graph only increases by a very small factor.
Only
Decreases by a very small factor. Thanks, yeah. And maybe one other way to think about this is okay, let's say I have 2 ghost edges in my cut, and that's all that's supporting this cut. Then, it has value at least k over 2 minus 8 at the end, so I'm happy, or k over 2 minus whatever order 1 I had here. If I have 3 ghost edges, you might be worried, okay, maybe I have 10 ghost edges, I'm missing out on order 1 times 10 now. But if I have 10 ghost edges, each of them has value k over 2. My connectivity is way larger than it has to be, right? It's 5k. And in that case, losing this order 1 factor actually doesn't have any effect. Okay, so yeah, cool. So we basically made it through it. So this gives us our main technical theorem. And there's some open questions. So the first is, I would love to improve this to k minus 1. I think it could be true. I don't know how, but yeah. The second thing is, this is, I think, a really nice fact. It says that like fractional connectivity and integral connectivity are basically the same, like up to a small constant. So I really hope it has applications elsewhere, wherever connectivity matters. Like one of the reasons I gave this combinatorics intro is I'm curious if there's a proof that kind of doesn't use LPs. Like this is just a fact. Like I've given you a fractional graph. Can you write it as an average of integral graphs that are, let's say, k minus 1 edge connected or k minus order 1 edge connected? Maybe there's a proof that like doesn't have to use, doesn't even know about LPs. Some induction or something. Who knows, right? I think that would be pretty cool. And finally, there's a nice open question that I think is really related to this problem, which is called the graph splitting hypothesis. And the question is, can we split any k-edge connected graph into two graphs that are close to k over 2 edge connected? Yeah, I think it's a very hard open problem, but I think potentially this could shed some light on it. So yeah, thanks a lot.
Yeah, a couple of comments. One, I
Sure.
think this is beautiful. You're using classical tools. You're getting a result that really feels I think it's a new classical result. I want you to turn back to the open questions.
Yeah, of course.
I really like question one. Another question is whether there is a trade-off between the number 10 and a little bit of approximation. Can you sacrifice a little bit of optimality and get that number down?
That's a great question.
On your question 3, I think the proof is beautiful. I think the other question is there an algorithm that's combinatorial or at least doesn't require, say, an ellipsoid type method? Something that could quickly do it. And finally, I've often wondered in iterative algorithms like this, I'm sort of hoping that they work well in practice. And I wonder how that would go. Because this LP is helping you out somehow, maybe the solutions you get in practice are actually much better.
Yeah, like k minus 1, you're saying. Okay, yeah. Those are
experimenting with.
Right.
If you could get some good instances.
Yeah, great questions. Yeah, that's interesting. Like, yeah, so can you boost up some edges and get k minus 1? That would be pretty cool. Yeah. Yeah, thanks. Other questions?
What's your kind of instinct why you believe that you can get it down to k minus 1?
Honestly, I don't know. I think it's just that, the only bad examples we have are these like really silly things, right? Like these, where did I put it? The triangle. like the only lower bounds we know are so easy. So maybe like these really are the only obstructions. But I think this is just wishful thinking. Like I have no real reason to believe
entirely.
it.
So there is a precedent. For example, in a problem where you're trying to find a minimum cost subgraph of bounded degree, there's a similar thing where you can get within one of the degree.
Right, that's true.
And your cost be less than or equal to the optimal.
Right.
So there's precedent for getting something that tight. So it would be a really nice result.
Yeah. I hope it's true.
There's also a precedent. I mean, for that, there is also a precedent of combinatorial algorithms too.
Yeah.
Whereas for this, there isn't. You're saying, but yeah.
Oh no, but I'm saying like.
Oh, for like question 3, maybe, yeah. Right.
Local search works, right? But then, so maybe there's hope for a that would make you hopeful for a non-open based algorithm.
Yeah. That's a good point. Yeah.
All right, we should get out. There's people in.
Thanks.